All right, let's get started. We'll continue density estimation from last lecture. So in this setting, you have a training set consisting of n data points. We assume that each xi is an element in Rd. It's a d-dimensional vector in the Euclidean space. And all the data points are sample IID from some distribution Px. However, the distribution is unknown. And we want to output P hat of x, which is an estimate of the unknown distribution Px. So the idea here is the following. Imagine D is 1 and you have data points that might look like this. You have some points here, some points here. Then you want a distribution that will assign, that might look like this. This might be your guess of P hat of x. So here, when the data points are more likely, you want to assign a higher value for the probability. And when they are less likely, you want to assign a lower probability. So we want to output a function P hat of x like the one shown here in the diagram. So the input here will be these 5 points and the output will be a continuous function like this, which is the probability density function from which the underlying data samples are believed to have been sampled. Okay, so here the input is some n points like this, and the output will be a function like this. That's the problem we are interested in studying. Last lecture we discussed two methods. One was the histogram based method, and the other was nearest neighbor. So we discussed two methods last lecture. Today we'll continue to discuss two more methods involving Gaussian distributions. So the main focus of today is to study a method known as Gaussian mixture model. Any questions about the setup? This is all review from last lecture. There is a question? Oh, sorry about that. A lot of students want me to videotape this, so I am myself trying to understand how to use these things. Any questions? All right. So we'll continue this today. The first method, actually before we go to Gaussian mixture models, is Parzen window estimator. So the idea here is that we will be using Gaussian kernels. A Gaussian kernel is basically the distribution of a standard Gaussian variable with zero mean and unit variance. So phi of z is defined as 1 over root 2 pi exp minus z square by 2. This is the PDF of a Gaussian random variable with zero mean and unit variance. Okay, I assume everyone knows this, have seen this before. If you haven't seen this before, then you should talk to us because this is a prereq for the course, ECE421 or equivalent probability course. Okay, so this function looks like this. Phi of z is a function of z. It's always positive. At z equals 0, it's 1 over root 2 pi, and then it decreases as you increase the value of z. This is a PDF of a Gaussian random variable with 0 mean and unit variance. So it's centered at 0, the mean, and it has a variance of 1. So the idea in this particular density estimation technique is to fit a standard Gaussian around each data point and sum things up. So if you are given a data set that looks like this, so imagine you are in one dimension and you have 3 points that look like this on the x-axis. Okay? What you will do is you will fit a Gaussian around centered. You'll take this Gaussian and shift it so it is centered around each point. And then you will sum up their contributions. So you'll have one Gaussian that might look like this, another Gaussian that looks like this, a third one that looks like this. They're all shifted now, so they are centered around those 3 data points, and you sum up their contributions. So then what you do is you add up them. So this is the sum. This will be p hat of x. It will be the sum of those 3 Gaussians. So at each point, you take the sum of this function. If you're at any given point, say this is the point you're interested in, then you take the value here, you take the value of this Gaussian and the value of this Gaussian. These two will be very small, so you'll actually be close to this value here. So you just sum their contributions to get this particular function. Mathematically, what you do is p hat of x in higher dimensions, you just take the norm values. So p hat of x will be 1 by k summation of n going from 1 to capital N phi, this phi function of the norm of x minus xi divided by r. So you take x, you take the distance of x from each data point. That's what this is. And then you evaluate this Gaussian kernel essentially at that point, but scaled by some constant r. So there are 2 new variables I have introduced here. One is k and the other is r. K is just the normalizing constant. So that these functions, when you take the integral of this expression, it is equal to 1. Because this is a valid PDF, you will not quite sum this. You will have to scale everything down so that the area under p hat of x equals 1. So, and that's the job of k. It's not too important. It's a simple constant. You can evaluate it analytically in this case if you want. We won't worry too much about exactly what k is. It's just some normalizing constant. Okay? R is actually the known as kernel width. It tells you how wide or how narrow these Gaussians will be, each individual Gaussians will be. So if you look at phi of z by r here, then if r is going to be large, what will happen to this function? Will it stretch or will it shrink? So imagine you are sketching phi of z divided by r, this r here. And let's say r is greater than 1. If I were to sketch this function on this particular plot, how will it look like? Will it be a stretched version of phi of z or will it be a shrinked version? It will be a stretched version, right? So if r is 1, the width is going to be larger. If r is less than 1, then the width is going to be narrower. So this function here tells us how wide a Gaussian we want to put around each data point. If this constant is large, then we are putting wider and wider Gaussians. If it is small, we are putting narrower and narrower Gaussians at each point. And what you do is you just sum them. So that's how we end up with this particular estimator. Any questions about this?
What is xi here?
x1, x2 up to xn are our data points. So I just wrote here. Here you have n data points that are given to you, and you want to produce a density estimate consistent with this n data points. So these, because you're summing from n equals 1 to capital N. So x1 will be the first data point, x2 is the second data point, and so on. So in this figure, you have 3 data points. So this will be x1, this will be x2, and this will be x3. And what you are doing is you are putting a Gaussian, you're putting this phi function at the center of each of the data point, and then summing it up. So this expression here is just mathematically representing what is being done in this figure. Yeah?
And so that x that's chosen on the figure, how do you get that one?
That's every point, every other point. So the idea is I'm going to give you a new point, and I want to know what's the density at this point. So it's a query point. Okay? For every point, this function is defined. So just so that we understand this, if you have a small value of r, the width, then you will have, and if these were your 3 points, your functions, your kernel functions might look like this, very narrow. And then when you sum it up, your p hat of x, it will be a scaled version of this, might look something like this. Because you're just taking the contribution of these 3 kernels which are very narrow. So when you sum them up, you will just basically equal this kernel here, maybe scaled down by the normalizing constant, but I'm not showing that explicitly. Then it will be 0 in this area because none of the kernels have any values here. They're all close to 0. Then it will go back around this. If you make r smaller and smaller, you will just get impulse functions at each point. So this is the case. When r is large, what will happen is, if you have these 3 points, you're going to put very wide kernels. This will be your Gaussians, very wide, right? And then when you sum it up, you might get something that is essentially insensitive to the location of x, because all the kernels will basically be such that the summation will be close to a constant with a small wiggle. So p hat of x will not show any much variation with respect to x now, because you have very wide kernels. Right? So of course these are extreme cases. The true thing will be somewhere in between, but this is roughly the trade-off between choosing small values of r and large values of r. So this corresponds to the left hand. Which of these corresponds to overfitting? Which one corresponds to underfitting? What about this one?
Overfitting.
It is overfitting, right? Because you are too sensitive to the location of points. You are putting very high probability where the points exist and very low probability where they don't exist. So you are being too specific to your data set. So this is overfitting, and this is typically underfitting. Now, how would you choose the correct value of r in practice? It's clearly a trade-off here. So how would you choose the correct value of r? Any ideas? Sorry? Let's say we have 100 points. How will you choose the correct value of r?
So we continue the r and until we see a minimum value there and it doesn't saturate. It's just more like a trend error.
Okay, but so something looking for something more specific. Yeah, so you want to choose. The thing is, if you choose r smaller and smaller, it will look better and better with respect to your training set, right?
Yeah, but I want to make sure that at least some point don't give a confidence of 0. Give a confidence.
It won't, because you're putting a Gaussian at each point. So every point will be properly accounted for. Except that if you take a very narrow width, it will look really well on your training set, because this is, you're putting high probabilities there. Yeah?
Is it related to the variance at all of the Gaussians?
Maybe, but again, this one is underfit. If you're overfitting, it's not immediately obvious, right? Both of them have, this is like not a single Gaussian. We'll have bumps around each point. And so the spread is not necessarily indicative. You could have two clusters here, and then you want to put mass there, right? So the variance is not the best measure.
How sparse they distribute?
How sparse they distribute.
They are close to each other, we can use a small
So you are saying we should accumulate close enough points into a single Gaussian. That's a good point. We will study that in the context of Gaussian mixture models. That's the next topic. But let's say in this model, we decide to put a bump at each point. So we want to be consistent with this rule, right? This is how we want to estimate the density. And the only thing we're allowed to vary is R. That's the problem. We don't want to change our model. So I'm giving you 100 points, maybe 1,000 points if you like, and it's one-dimensional, and all you have to do is find the correct value of R. Based on what you know so far in the course, what method will you use to find the right value of R?
Every testing set. So make sure we have E out to compare with.
How do you compute E out?
Keep some.
Okay. So people are saying maybe we should use validation. Can anyone crystallize how we will use validation? Be precise as to how would you go about selecting R using the validation method that you did in assignment 1, assignment 2, and so on. Yeah?
Maybe we like gradually tweak R and then check your validation as well as your training and see if the difference is too huge. If it's like very, very huge, then probably increase your R.
So what do you mean, well, what are you going to compute? We said difference, right? But what are you going to compute? We haven't even said what the loss function is here. So what would you compute on the validation set? The goal here is, like, there are no labels. So it's not like you're computing the squared error or any obvious metric like that.
Like the difference between the, like, if you actually plot the distribution of like the X point that you're given, and then also plot it with the validation data, and then you just see what's the difference between each point.
So you're saying we should compute this function twice?
Yeah, once using the actual training data, once using the validation data, and then seeing what's their difference.
I see. So that's for possibly one method we could consider. So the suggestion was, let's say you divide the data into 50-50, put half of 1,000 points, put 500 for training, put 500 for validation, and for each one compute. So compute p hat 1 of x with respect to the first set, p hat 2 of x with respect to the second set. Now you have two functions and see how close they are, right? If you're overfitting, then those two functions might look very different. If you're underfitting, what would happen? It might just look like a constant in both cases. So it doesn't quite solve it. It might bias towards this thing here, right? It might just, the constant you have, the better. Like if you just have a flat thing, then in both cases, if you have very large variance and you're getting a flat distribution, it won't be able to distinguish. It's a very good try, but it doesn't quite work. So I'll tell you what the answer is. Any other suggestions?
Use the data in 80%.
Okay, and what do you do with the 20%?
Then you validate from 20%.
How do you validate?
Like for each point you compute, and is it like good enough as like particular or very error is similar?
Which error? So any
Again, the
other?
difference.
Maximize log likelihood. That is actually the right answer. So what you do is, given p hat of x on the training data, let's say your validation set consists of points like this, x1, x2 up to xm. This is your validation set. And let's index this by r, the width, right? That's the parameter we want to optimize. What you do is you compute p hat r of x1 to xm. So this is on your validation points, right? So let's say m is 200. We put 200 points in the validation set and 800 points in the training set. So x1, x2 up to x200 are the points in your validation set. Then what you do is you compute the probability assigned to these 200 points in the validation set. So this one will be the product of I going from 1 to m p hat r of xi, because we assume that the data points are sampled IID. That's how we started with. So this is the probability we will be assigning to the validation set. Okay? So these points were not used in training. The rest of the data set was used in training. That's how this function was computed. For each value of r, you can compute this. Right? And then you select r to maximize p hat r x1 to xm. So you want to choose an r that assigns the maximum probability to the data you have not seen yet. If you are underfitting, you're going to assign less probability. If you're overfitting, you will assign less probability. If r is just right, you will assign the highest probability to the data you have not seen. And as was suggested, instead of this, we can maximize the log of p hat r of x1 to xm. So this is the summation of I going from 1 to m log p hat r of xi. Maximize this. This is known as a likelihood estimator, because you're maximizing the sum of the logs. So that's what you do. Anytime you have a hyperparameter that you want to select, there is usually the one thing to do. Look at the validation set and see which value of the hyperparameter performs best on the validation set. Sometimes the hyperparameter is a regularization constant, right, as we saw in least squares. In this case, it is the kernel width. It is something which is critical to select, because you can either get overfitting or underfitting if it is not selected properly. But then a natural way of selecting the right R is simply through using a validation set and maximizing your function here. In this case, it's the likelihood function, the log likelihood function on the validation set. Any questions?
Can you explain the part where the problem underfitting can make from that question, and that can be solved? Like what if the data are underfitted and
If the data is underfitted, you will have something which is nearly constant. So all the points will have low probability. What you imagine, you have a data set that looks like this. Okay? Then you want to assign high probability here, and you want to assign high probability here. What the underfitting thing will do is it will assign something uniform across everywhere, which is the wrong thing to do. You don't want to do that, right? So even if you're getting points here and here, then the underfitting will just assign everywhere a small probability, because it's just uniform. So in this case, what you want, the correct distribution would have something which is highly clustered here and here. And so the right value of R will do that. It will, in a sense, someone was mentioning before, accumulate the contribution of this into a single bump and the accumulation of these points into a single bump. So that will give us the right value of R.
Why do you want to maximize that probability?
Because this is, so we are computing, intuitively, we are computing the correct density that gives rise to our observed data samples. That's what we want to do. In the density estimation problem, you get data points, say you get 1,000 data points, and you want to say, okay, I want to find the density function that is responsible for generating these data points. Okay, so now what will happen is, for each, I have two sets. I have one set that I have not seen and one set that I have seen. So I do training on the set that I have seen and compute the density function. Now I want to know how good it is on the data set I have not seen. So I compute the probability of the unseen data using this density function. If it was truly responsible for generating the data set, it should also assign high probability to these points. Is that clear? Otherwise, you will get less, it won't explain. So the true test of this density function will happen when you evaluate it on the data you have not seen. Now, what we are doing is we're just providing a probability density for responsible for generating our data. So we want to find a function that explains the unseen data as well as possible. So mathematically, it is that it assigns the highest probability to this data set. Is that clear?
Just make is the overfitting model is the same height as the underfitting model at the peak? Even
The area under all the probabilities will be 1. The heights are never important in density functions.
So does that mean the second model, the underfitting model, will be more? Everything is low.
Yeah, it will be. I just cannot draw it on the figure, right? But yeah, it will be scaled down. It will be somewhere here. So area under it is 1. I'm just giving you the qualitative picture of what happens. Otherwise, it will look very complicated if I start drawing this here and so on. But you always pull it down so that the area under each function is 1.
How exactly do we select the parameter? You said we need to select it to maximize the likelihood, right? But how exactly do we test it?
Well, you just vary R, right? From a small value to large value. In each case, plot this thing.
But how many of them possible?
You just made one plot because R is a scalar here.
Yeah, but like for each item.
For each R, so R is on the x-axis. So let's say this is R, and the y-axis is the likelihood function. It is p hat of R on the validation set. What will happen is it will be low, it will increase, and it will then start decreasing again. And this is the R that you want to select. I don't know what the question was. But. Any other questions?
Like, wouldn't this lead to overfitting of the validation data?
But you have not seen the validation data. I don't know what it means, overfitting of
like,
the validation.
I mean, like, because you're using the validation data to find your R, essentially.
Right.
Right. But like this R is specifically for the validation data. So why is it like not I guess to a degree overfitted towards the validation?
So I think what you are saying is that the test error evaluated on the validation data is not the actual estimate of the test error because the choice of R is biased with respect to the validation data.
Yes.
That's a great point, and we will develop precise bounds, theoretical bounds on how much the penalty is in this process in the next topic, which is pack learning, which will start next week. So if the bottom line is if you choose your validation data to be large enough, the bias that you get from the choice of R will be very small.
Okay.
So it won't be, if you have 200 points and if you're training one scalar value of R, the bias you get won't be such big, and your estimate for the test error will be close to the true out of sample error.
Okay.
So that works, but so precise theoretical bounds will be derived when we study pack learning.
Okay.
So the point was, which was an excellent point, is that now your R is selected with respect to the validation error. So you're introducing some bias in the choice of your R with respect to the validation set. So if you compute your error test, if you want to estimate your test error, then the error you compute on the validation set will no longer be a true estimate because R is biased with respect to it. And that's a great point, and we will discuss these issues at length when we discuss pack learning. But at this point, the rule of thumb is that if your validation set is large enough, this won't be a problem and you don't have to worry about it. There is a generalization to validation called cross-validation, where we will revisit this, which is a much more efficient method than validation when you have a limited amount of training, and again we will see these trade-offs in that context. All right, so move on to the next topic, Gaussian mixture models. So imagine that your data set is in 2 dimensions, and this was something that was just made up by a student before, but just the motivation was already there in our discussions. Imagine you have 2 data points, like each data point is in 2 dimensions, sorry. You have your data, if you plot your data set in 2 dimensions, it looks like this. Okay. Now what the previous estimator would do is it would force a Gaussian kernel at each of the data points and sum up their contributions. And that's typically an overkill if you have thousands of data points. Putting a Gaussian at each data point and summing its contribution is computationally expensive and clearly not needed. Here I think it is very clear that there are just 2 Gaussians, one responsible for this set and another responsible for this set. So only 2 Gaussians are sufficient. So one from which this set of points is sampled and another from which this set of points is sampled. So there will be a mean associated with this Gaussian and a covariance matrix associated with this Gaussian, and similarly there will be another set of parameters associated with this Gaussian. So here, for example, the intuition is if I want to sample a new data point, I'm going to first flip a coin, maybe 50-50. The coin will be such that with probability half you get a heads and probability half you get a tail. If it is heads, then I sample data points from this distribution. If it is tails, I sample data points from this distribution. To sample points from this distribution, I just use the Gaussian with the mean and covariance and then sample from that distribution. Is this clear? So we are not trying to now force a Gaussian at each data point and then sum. It's usually computationally very expensive to do that. There are just too many terms. Here we will only have 2 terms, one corresponding to each Gaussian. So for this, we need to introduce the terminology of multivariate Gaussian distributions. How many of you have studied multivariate Gaussians before? Can you raise your hand? You have seen multivariate Gaussians? Very few students. I think this is a topic in 302, one of the topics you have to do, I think. It is in the course description, I believe. So, how many of you have done bivariate Gaussians? When you have 2 variables? Not many. You have to speak to your instructor and see if it was really done or not. Okay, so we saw the units, the standard normal distribution. Okay. Now there is a generalization of this. If Z is Gaussian with mean mu and variance sigma square, then Fz is 1 by root 2 pi sigma square under the square root exp minus Z minus mu square by 2 sigma square. I hope everyone has seen this. Okay. And so this is basically the same that we saw before, Fz as a function of z. Sometimes I write the subscript z to denote the random variable. In this case, I will. Okay. And the idea is it is centered around mu. So it looks like this. And the width here is governed by sigma square, so variance. If sigma is large, the variance will be large. If sigma is small, it will be peaky. So here the mean equals mu, the variance equals sigma square, the standard deviation is sigma. Okay, everyone knows this? Okay. So I don't think I should spend time having you write this because everyone knows this, right? This is not important. Okay, now let's do bivariate Gaussians. These notes are available, will be available afterwards. So if you missed that, you can copy it later. What's a bivariate Gaussian? Well, suppose x1 is a random variable which is Gaussian with mean m1 and variance sigma 1 square. And x2 is a Gaussian with mean m2 and variance sigma 2 square. We have two random variables. And I can compute the covariance between x1 and x2. So covariance is defined as the expected value of x1 minus m1 times x2 minus m2. And that will be, let's say, sigma 1, 2. So x1 is a Gaussian with mean m1 and variance sigma 1 square. x2 is a Gaussian with mean m2 and variance sigma 2 square. And I want to see how correlated x1 and x2 are. So I compute a covariance between x1 and x2, which is the expected value of x1 minus m1 times x2 minus m2. Right? I can compute this, and let's say that is sigma 1, 2. There is another quantity called autocorrelation coefficient, which is rho, which will be sigma 1, 2 divided by sigma 1 times sigma 2. It's just a normalized covariance, very normalized by the standard deviations of the two random variables. It is known by something called the Cauchy-Schwarz identity that rho is between minus 1 and 1. Assume all this is familiar to everyone. You have studied covariance between two random variables, mean, variances, and so on. Nothing is new here. If this is new, then talk to us because I think you will have a fair bit of catch up to do. Now, if we look at the density of x1 and x2, if x1 and x2 are jointly Gaussian, then the density can be expressed in terms of the correlation coefficients and the means and covariances. And this is given by the following. It's exp I'll continue here. This is the formula for the joint density of x1 and x2. It involves the mean and variance of the two random variables. And this is the whole thing, right? So I should guess the way I have written may not be clear. So you're taking the numerator. So you're taking this whole expression and dividing the whole thing. So this is the whole term inside the brackets, and you're dividing it by 2 pi sigma 1 sigma 2 times 1 minus rho square. Everything inside these brackets is divided by 2 pi sigma 1 sigma 2 times square root of 1 minus rho square.
So what is that to do with this fx x1 x2?
This is f of x1. Sorry?
Sorry, how did you call it? fx1 x2?
It's the joint probability density function. Joint PDF. Does this ring bells? I was told by the 302 instructor that this was covered, at least when they taught it. That is true. The good news is you won't need to know these formulas in great details in this lecture. Yeah? Oh yeah, good point. Someone remembers things. That's nice. Yes, there is a row here. Okay. All right. So this is the joint PDF. Now, if you sketch it, if you look at the geometry of this, so let's consider the case when f of x1, x2 is a constant. So you want to find the locus of all points where the PDF is a constant. If you stare at this for a bit, then you see that the only dependence on x1 and x2 is inside these brackets. Right? So this is equivalent to saying that x1 minus m1 divided by sigma 1 square plus x2 minus m2 divided by sigma 2 square minus 2 rho x1 minus m1 by sigma 1 x2 minus m2 by sigma 2 is a constant. So if you want to do the contour plots of the joint PDF, it's equivalent to having this function of x1 and x2 to be a constant. Now it so happens that this function has a special form. It's quadratic in x1 and x2. This is actually an equation of an ellipse. So if you were to sketch this in the x1, x2 plane, then the ellipse would be centered at m1, m2. The joint PDF will be highest when you are at the point m1, m2. So this is m1 and this is m2. And if we were to look at the locus of points where this function is a constant, it will be an ellipse. So it will look like this. This is an ellipse, a set of points where f of x1, x2 is a constant. As you increase the constant, these ellipses will become bigger and bigger, but they will be all concentric and centered around m1 and m2, the two means.
Does the line necessarily go through the origin?
Not necessarily, no.
And is the distribution on the probability axis uniform, or is it still more like a smooth?
The distribution on this axis here,
we do have an axis that points upwards, right?
so the function is coming out of this plane.
Yeah.
Right.
Yeah, so is this uniformly distributed, or is it sharp?
On the ellipse?
Yeah.
On the ellipse, it has the same constant.
Okay, sharp.
So it will have the same value. The function will be coming out here from the board along the third dimension. And if you want to find a slice of the function where it is constant, that slice will always be an ellipse like this. Okay? On that ellipse, the function will be constant. So if you condition on the fact that x1 and x2 are on the ellipse, then all the points will have the same probability on the ellipse because it's a contour plot. The orientation here depends on rho, on the value of rho. We can compute it. If rho is 0, then this becomes just a vertical. The orientation here, and you can compute, if you know your basics, you can compute this angle in terms of rho sigma 1 and sigma 2, but we won't do it. If you can see Leon Garcia, the textbook, for more details. So this is in the textbook by Leon Garcia, page 238. If you need to review this, this is the best book to look at. I think all of you have it as a textbook. So, and this week's tutorial will also do this in detail if you have missed any of it. So don't worry too much. Now you can extend this to multivariate Gaussians to more than 2 random variables. Typically, we will be operating in d dimensions instead of 2 dimensions. So we have to extend this definition to a d-dimensional Gaussian vector. So in this case, our vector will consist of x1, x2 up to xd, where each xi is a Gaussian. And all the xi's are correlated. So in this case, we take expected value of xi to be mi, and mu, which is the expected value of the vector x, to be the vector m1, m2 up to md. Put a transpose here, they are all column vectors. So this is the expected value of x. The other quantity is the covariance matrix. The covariance matrix will be denoted by sigma, and it will be a d by d matrix. Its entries will be like this: sigma 1 1, sigma 1 2, up to sigma 1d, sigma 2 1, sigma 2 2, up to sigma 2d, sigma d1, sigma d2, up to sigma dd. And sigma ij is just the covariance between xi and xj. So it's xi minus mi times xj minus mj. So for the Gaussian vector x, you are defining its mean, which is a d-dimensional vector, and each element is just the mean of the corresponding element in this vector. So x1, x2 to xd are individually Gaussian. The mean is mi here for the ith variable. So that's how you get the mean vector of x. The second quantity you define is the covariance matrix, sigma. And sigma is a d by d matrix, right? So sigma is in R, d by d. It's a symmetric matrix actually, because sigma ij will equal sigma ji, because the covariance function is symmetric between I and j. And its entries will look like this. So sigma ij is expected xi minus mi times xj minus mj. So that's how you can compute all these entries. Now the PDF for the vector x is defined as follows. Fx of the vector x, and I will not write a subscript now. Fx is given by one over 2 pi raised to d by 2 square root of the determinant of sigma times exp, the exponential of minus x minus mu, the vector x minus mu transpose sigma inverse x minus mu by 2. This will be the PDF of the random vector x. Again, it depends on the mean and the covariance matrix sigma. This is a generalization of the bivariate Gaussian density function to a d-dimensional Gaussian vector. It has the exact same interpretation. If you look at the locus of points where fx is constant, it's this function here, x minus mu transpose sigma inverse x minus mu to be a constant. And if you plot them, it will be d-dimensional ellipsoids. And in this case, the axis of the ellipse will be the eigenvectors of this matrix sigma. You can easily characterize the directions where you had those major and minor axes just come from the eigenvectors of this matrix. So this is reviewed on page 240 in the Leon Garcia text. This is just if you substitute d to be 2 and evaluate this quantity, it will coincide with the definition for the bivariate Gaussians.
So when you started writing this, you assumed that all the xi's should be mutually correlated.
Yeah.
Why do we need that assumption?
Well, this includes even if they are independent, then all the off-diagonal terms will be 0, and this would just then be a factor.
That would be a special case. For the purpose of what we were doing before, we have to consider the general case.
Yes. So for this here, the orientation of the points usually will require a Gaussian where the ellipses are not spherical. They will be oriented. Whenever you have oriented ellipses, then the underlying variables are by definition correlated, right? If they were if x1 and x2 were independent, then this would be a spherical Gaussian. That would just be a sphere around that cluster. But that's usually not the case. You need the orientation for the maximum fit. So we have to consider correlated Gaussians here. And that's why this matrix is important.
We are calculating the norm of the covariance matrix. Which norm is
This is a determinant, not the norm. And this matrix is what is known as positive semi-definite matrix. It has a special property. If you take more advanced courses, all its eigenvalues are positive. It's something that comes out because of the square, because this is of this form. You can show that it is not only symmetric but positive definite. So this determinant is always positive. Like so, the square root is well defined. Okay. It's because of this chapter that 302 is a prerequisite, by the way. So we'll give you some practice with Gaussians in the tutorials this week and next week. All right, so now we have Gaussians. We will use the following notation for x. For this x, we will use the notation that x is Gaussian with mean mu and covariance sigma. So this is the notation for a multivariate Gaussian. This is the mean and this is the covariance matrix. And the idea here is that once we have this, it's implied that fx is 1 by 2 pi to the d by 2 square root of the determinant of sigma exp minus 2 x minus mu sigma inverse. So you can immediately, once you have this notation, you immediately know the PDF of the Gaussian vector x. So one-to-one relationship between this notation and this notation here. All right, so we'll use this as a shorthand. We have seen this in the case of scalar variables, where this was the mean and this was the variance. This is a generalization when x is a random vector with d entries in it. Now you have a d-dimensional mean and a d by d dimensional covariance matrix.
Should it be x with underbar?
Yeah, all of those are underpass. Okay, there is an inverse here. This is not sigma, it's a sigma inverse because the variance goes in the denominator in the exponential. So I will let you study this. If you have not studied before, we'll move on to machine learning. This is not a course in probability after all, it's a course in machine learning. So we'll move on to what we need in machine learning. So we will next define the central PDF, the class of PDFs that we are interested in, which is a Gaussian mixture model. This is the class of density functions. We are not interested in pure Gaussians. That is usually too restrictive. We are interested in a generalization of Gaussian density functions, which is Gaussian mixture model. Okay, it's one step beyond multivariate Gaussians. We want to make things more complicated. Okay, so the idea is the following. Imagine that you have data, your data set looks like this. Right? Then you want to intuitively say that this is arising from three Gaussians. One that explains this cluster of points, one that explains this cluster of points, one that explains this cluster of points. So you want to put one density function here, one density function here, and one density function maybe here, and sum them up. You don't want to have a density function for each data point. You just want one that explains this spread, one that explains this, one that explains this, and you want to sum them up. Now you want to control their heights proportional to the number of points. If you have more points, this is more likely, so this should have a higher weightage. This is fewer points, it's less likely. And so p hat of x should now look something like this. Right? It should be the sum of all these different densities. So if I were to, so the actual p hat of x will not be a Gaussian. It will have multiple bumps. Right? It will look something like this. So I'm saying my density, my data points are sampled from this distribution here, which is basically consisting of three Gaussians added together, weighted by some weights that tell us how likely each one is. So it looks something like this. So this is an example of a Gaussian mixture model. So here, so this is in one dimension. So this could be, let's say, 1/4 times a Gaussian with mean mu1 and variance sigma 1 square. This could be 1/4 times Gaussian with mean mu3. So these are the weights that I assigned. And this here is 1/2 times Gaussian with mean mu2. So I'm going to scale them by some amount, which tells me intuitively how likely each one is. So here I scaled this by 1/4, Here I scale this by 1/2, this by 1/4. So they have different heights now. And then I sum them up. So the actual distribution is 1/4 of this plus 1/2 of this plus 1/4 of this. That's how I get this distribution. Okay. So in this example, any questions about this?
The choice of picking 3 models is by us.
It's just arbitrary, right? I'm giving you an example, right? I'm giving you, suppose I have a data set like this and I want to fit a Gaussian mixture model. Then I want to put one Gaussian here and I want to figure out what the mean and variance is. That tells me how much spread this function has. Another Gaussian here and a third Gaussian here. And then when I compute the actual density, I take a weighted sum of those 3. Any other questions? So in this example, if I were to write p hat of x, it would be 1/4 times 1 by root 2 pi sigma 1 square exp x1 minus mu1 square, the minus, plus 1/2 1 by root 2 pi sigma 2 square exp x minus mu2 square by 2 sigma 2 square plus 1/4 1 by root 2 pi sigma 3 square exp minus x minus mu3 square by 2 sigma 3 square. That's mathematically what the figure we saw on the previous slide. We are taking a weighted sum of 3 Gaussian density functions. I will write this just for a compact form, in a compact form, as 1/4 times Gaussian. Now I'll actually write the variable just to emphasize x is the variable. Mu1 sigma 1 square plus half Gaussian x mu2 sigma 2 square plus 1/4 Gaussian x mu3 sigma 3 square. Just a short form for the previous form. These are all equivalent. I can draw that figure that sums them up, or I can write this analytical formula, or I can write it in short form in this way. They are all similar. And this is what is called a mixture of Gaussians. Or a Gaussian mixture model. Questions about this?
Is it always true that the weight we choose are based on the number of data?
We will figure out. No, this is just one ad hoc choice. I'm giving you one possible example of a mixture of models. So how do you choose the weights? How do you choose the means and variances? These are all our model parameters. And we will figure out a way to properly select them. So to understand this quantity, so to understand what this Gaussian mixture model is doing, imagine that you have to sample a new data point. So you want to sample a new data point. Let's call this data point. Then you have 3 possibilities. You have a Gaussian with mean mu1, variance sigma 1 square. You have a Gaussian with mean mu2, variance sigma 2 square. And a Gaussian with mean mu3, variance sigma 3 square. There are 3 possible Gaussians you have. You have a switch here such that your switch can select one out of these 3 branches. There are three possibilities, three possible Gaussians you can use to sample any given data point. Your switch connects to the first one with probability 1/4, the second branch with probability half, and the third branch with probability 1/4. Okay, there are three possible Gaussians you can use to sample. Now, every time when I want to sample a point, I don't know which Gaussian I will use. I will make a probabilistic choice. I will go to the first branch with probability 1/4, second branch with probability half, and the third branch with probability 1/4. And then I'm going to output, and this is how I get my data point x. This is scalar, so no bar. So to sample the data point x, I'm going to decide probabilistically which Gaussian to take. And that probability is determined by the weights of those three Gaussians. If I decide to go on the first branch, then I'm going to use this density here to sample, and most likely I will be in this cluster here. If I use the second branch, I go into this Gaussian here, and most likely I will belong to this cluster. If I use the third density, I will be somewhere in this region, right? Now, I won't be deterministically at any one point. It's a probabilistic relationship, both in how I select the branch and which point I ultimately output from that density function. So there are two levels of randomness. Any questions? So now we will just formalize this definition for multivariate Gaussians and then take a break. So the idea here is that the Gaussian with mean mu j and covariance sigma j, this is the jth Gaussian. And we will use the notation p sub j of x to denote the jth Gaussian. Okay? Then p hat of x is given by w1 p1 of x plus w2 p2 of x up to wk pk of x. Imagine you have k Gaussians, then this is the summation of k going from 1 to k, wk pk of x. Wk is the weight associated with pk of x. Okay, this is the probability of selecting pk of x when we do the sampling. So it's the probability we go to the kth Gaussian in that branch. That's what wk. So all the wk will be positive and the summation of wk will be 1. This is how the weights are selected. Once we select the weight, we take that and multiply it with the Gaussian density function, the multivariate Gaussian, evaluated with respect to the kth density. And then we take the weighted sum. This is just a direct generalization of the scalar case we saw before. A weighted sum of the Gaussian density functions. Each function is now not a scalar, but a multivariate Gaussian with mean mu and covariance sigma. So the idea is that if you have two clusters like we had before, and you will have say some points like this, and you will have a Gaussian here with mean mu1, covariance sigma 1, you will have another Gaussian with mean mu2 and covariance sigma 2, and your actual density will be a weighted sum of those two. If the weights are half and half, then with probability half you end up in this cluster and you sample using this density. With probability half you end up in this cluster and you sample with this density here. That's the idea. Any questions? So I will let you take a 10-minute break. It's 7:24, so we'll start at 7:34. And if you have questions about this, you can come and ask me in the break. Yeah?
And this model is more like a fine-grained k-means because it sounds like they are solving